In this video, we will talk about pressure and hydraulics. And we'll start with pressure. We know that the definition of pressure is force in newtons over area. Oh, that was weird. Area in square meters. And a newton per square meter is a Pascal, named after Blaise Pascal, the French physicist. The abbreviation for Pascal is simply PA. Let's do a quick example. Let's suppose we're talking about me. I'm at my standing desk right now, and let's find the pressure of my feet on the ground. So the pressure is going to equal the force over the area, and the force that I exert on the ground, if I were to create a force diagram for me, the force that I exert on the ground is my weight. So the Fg is going to be mass times 9.81, which is approximately 70 kilograms times 9.81. And now I have to figure out the area, the area of my feet. I'm wearing running shoes today, and this is not the greatest picture, but it looks kind of like that. And I was kind of looking at my feet and thinking, well, actually, if I put my 2 feet together, it kind of looks almost like a square. And it's about 25 centimeters on one side, or 0.25 meters. So the area would be 0.25 meters squared. So I'm going to take 70 times 9.81 divided by 0.25 squared, and I get 10,987 pascals. So that kind of gives you an idea that the pressure of my feet on the ground is about 11,000 pascals, just to give us an idea of what that actually feels like. Okay, so we can apply pressure to a situation called hydraulics, which evidently, there we go. Now, in hydraulics, what we have is a piston. A piston, just a single piston, is simply a cylinder on the outside. And then on the inside is what we'd call a piston. And you can push down on the piston and create more pressure. Later on, we're going to study thermodynamics, and we'll be talking about gas inside of a piston. But for right now, we're going to assume that the piston has liquid inside of it, and that liquid is incompressible, which means that the density is constant. In other words, the density doesn't go up when the liquid is compressed. Now, in reality, that is kind of an invalid assumption. Like at the bottom of the ocean, the density increases with depth. But since this is an introductory course, we are going to keep it simple and assume that density is constant. Okay, so in a hydraulic system, we actually have 2 pistons. We'll have a smaller one attached to a larger one. And the system is closed, so there's no way for anything to get out. So I don't want to get too artsy here, but I don't want you to think there's any holes. There's no holes in this system. And we have 2 different cross-sectional areas. So here's cross-sectional area 1, and here's cross-sectional area 2, and they're different. Here's what's the same. The pressure on both sides of the hydraulic system is the same. The pressure is the same, even though the forces in the areas are different. So what's going to happen is, on this side, on the left side, actually, let me move this over a little bit. On the left side, I can exert less force. I'll make a smaller red arrow, and I will get out more force. This is intended to be a bigger arrow. I don't know how well I'm doing here. I will get more force out on the right side. Why would this be so? Well, if pressure on the left equals the pressure on the right, then the force over the area on the left equals the force over the area on the right. And in order for these ratios to be the same, like let's say this ratio is 2/1, to keep the ratio on the right the same, say it's 4/2, when the area goes up, the force goes up. How can that be? How can I get something for nothing? Well, we know from physics that we can't get something for nothing. So what ends up happening is the volume of fluid that's pushed through the system, when it gets to the fatter side, it's much, much thinner. Maybe this isn't my best picture. I'll make this even a little bit fatter. So this volume of liquid on the left, when it gets to the right, it's got to be thinner because it's got a bigger cross-sectional area. So the distance that you push the piston is also not the same. And what happens is, on the right side, you get more force, but you get less distance. And in fact, if there's no friction, F1 times D1 should equal F2 times D2. This would be conservation of work. So that's pretty cool. The other point that I should make is that volume is conserved. So volume on the left equals volume on the right. And just a reminder that the volume of a cylinder would be its cross-sectional area times its height. Here I'm calling the height distance. So that is conserved as well. Okay, so I'm asking you to do a lab with, with a video that I made, because we can't be here right now. And in that lab, what I'm asking you to look at is a video of me working with some pistons. They're actually syringes. And then I ask you to make a graph of F out, which would be F2, over F in, which would be like F1. And the graph's going to look something like that. And I want you to keep a couple of things in mind here. First of all, this y-intercept is due to friction. In AP Physics 2, we idealize things, but then when we do labs in real life, our idealizing doesn't really work. So there is indeed friction. There is a minimum amount of force I have to exert to get that piston to move. Now let's ignore that for a second though, and let's just look at the slope. Slope is rise over run, which is going to be the output force over the input force. And this is where I get a mechanical advantage. If I have an output force of 4 and an input force of 2, I'm getting more force out than I put in. And again, that's called mechanical advantage. If the numbers were 4/2, the mechanical advantage would be 2, meaning I get twice as much output force. I can take this formula, the one that's based on equal pressure, and I can rearrange it. And what we want to do is we want to try to write a formula of the form y equals mx plus b. And so in this case, F out or F2 is like my y, right? That's on our y-axis. And F1 is our variable that's on our x-axis. So I'm going to rearrange this a little bit. I'm going to multiply both sides by A2. And then I'm just going to turn this around. So I'm going to write F2, so I'm starting with this, equals A2 over A1 times F1. And the point of the lab is for you to think about, what does the slope mean? And again, we've got y equals mx plus b. Here's your y-intercept, b. And look what the slope represents. The slope represents this ratio of areas. The ratio of areas of the two pistons. And that's something you should be able to determine in the lab. So I'll be curious to see how this turns out and if it works. Let's do one example. We'll just do one really simple example. Let's say I have a car on a hydraulic lift. Oh, I missed a U in hydraulic. And the car has a weight of 12,000 newtons. And it's on a piston of 0.9 square meters. And I'm going to push on the other piston with an area of 0.2 meters squared. How much force do I need? Okay, so again, I'm going to sketch the situation. I'll just kind of go fast here. Again, I'm going to push over here. This is the small side, 0.2, area is 0.2 square meters. My force is unknown. And over here, I've got a car. I don't know if you've ever gotten to take your car in to get an oil change. And they lift it up on this hydraulic lift. And how do they do that? They use pistons. So the area over here is 0.9, and the force needed is 12,000 newtons. So I'm going to use my formula, F1 over A1 equals F2 over A2. So I've got my unknown force over 0.2 equals 12,000 over 0.9. And when I solve that, I get 2,670 newtons, which is roughly 267 kilograms, which for me is still too heavy to lift, but I did reduce my force by quite a bit. Okay, see you in class.